Physics chapter 24 theory video 3. Now we are going to deal with currents crossing fields. So now you know that when current passes through a conductor, there is a magnetic field that is created. When that magnetic field is in another magnetic field, there will be a force generated because of the interaction of the two. Then if this current carrying conductor is placed in a field like this at right angles to the other field, then there is a force generated. So at this point there is a force generated downwards, then there is a force upwards here. So then this results in a torque that is being torque to be resulted. That means it will rotate, because one side will be pushing downwards, the other side will be pushing upwards. As a result, from two ends, as a result it will rotate. So this rotation can be used to make a motor, and that is the basic principle behind motors. So now let's see how this worked example explains these details and how they can ask questions out of this. An electric motor has a rectangular loop of wire with the dimensions shown in figure 24.19. The loop is in a magnetic field of flux density 0.1 Tesla. The current is 2 amperes. Calculate the torque or the moment that acts on the loop in the position shown. So they are asking for the force that would be generated as a result. So let's see how this is going to how this can be calculated. So first of all, we have to write down the quantities that they have provided. So they have given the flux density or the B of the field. So then B is 0.1 T, then I is equal to 2 amperes, they have given that, and L is 0.05 meters. 0.05 meters, because that is the length of the wire in the field. So that is 0.05 meters. That is the length of the wire in the field. So we don't add them together here, because then it would become 2f, right? So we simply take f. As a result, the length of the wire in the field is 0.05 meters. Now we can B, I, L, all three are known. So as a result, we can find out the force. F equals BIL. B is 0.1, I is 2 into 0.05. That gives us 0.01 newtons. The two forces are on opposite sides of the loop, and they are anti-parallel. That means they are parallel but in opposite directions. They form a couple. So that results in the torque or the moment of a couple is equal to the magnitude of one of the forces times the perpendicular distance between them. So that is the torque that we are going to refer to, right? Torque or the moment of a couple is equal to the magnitude of one of the, moment is perpendicular distance into force, magnitude of one of the forces times the perpendicular distance between them. The two forces are separated by 0.08 meters. That is something they have provided, right? So they have provided that they are separated by 0.08. So as a result, what we do is we multiply to find the torque, we multiply the force by separation, 0.01 into 0.08. That gives us 8 into 10 to the power 4 Newton meters. If you have any difficulties, ask questions. If not, do the question 10, 11. But before that, please write down this note. When a conducting loop of circuit is placed in a magnetic field as shown below, a torque is generated which can be used as the basis of electric motors. Right. Now moving on to the other one. So now that was when it is placed at 90 degrees. Now we are dealing with any other angle other than 90 degrees. So here you can see in this setup, we have placed it in other angles from A, B, C to D, right? At D, when it is placed, it does not cut the magnetic field at all, right? But in other situations, they cut the magnetic field. Now we have to deal with this theta angle. So this theta is something that you need to understand properly. This theta is with the horizontal, the angle with the horizontal. So now let's see how it is going to be. Now we know that if it is now in the earlier whole experiment, we knew that if it is not at 90 degrees, the B is going to be, flux density is going to be lesser. So then as a result, what happens is from OA means this point, it would show the highest force that can be generated. Then OD would be, because it does not cut any of the field lines, there wouldn't be any force that is generated. But between these two, 0 to the maximum, it increases from here to here. Then the other fields, that is OA is the maximum, OB and OC, they would have values, but they would be lesser than that of OA, right? So for this particular scenario, you have to use the FB sine theta IL or else FBIL sine theta, because they are all multiplications. We can include sine theta anywhere. So this theta is the angle between the magnetic field and the current or the conductor, right? Between the magnetic field and the conductor, right? So then FBIL is what we refer to. FB sine theta. As a result, you know that sine, if it is the separation 90 to 0, the conductor, and the angle here it is 0 to 90 is the separation. So now let's look at the example here. A conductor OC, see figure 24.2, of length 0.2 meters lies at an angle theta of 25 degrees to a magnetic field of flux density 0.05 T. Calculate the force on the conductor when it carries a current of 400 milliamperes. First of all, we need to write down everything that we know. B has been given as 0.05 T. L is 0.2 meters. You be very careful when figuring out L. This L refers to the length of the wire in the field. Then I has been given as 0.40 amperes. Convert that into amperes. 400 milliamperes is equal to 0.40 amperes. Then theta is 25. They are asking for F. We need to use the equation because we know the equation. F equals BIL sine theta. B is 0.05 into 0.4 into 0.2 into sine 25. That would give us 1.7 into 10 to the power minus 3 newtons. Now we have to give the direction of the force. Why? The force is going to act at 90 degrees to the field and the current. That means perpendicular to the page. The left hand rule shows that it acts downwards in the plane of the paper, right? So that is giving the direction. component B parallel to current, the component of B parallel to current B cos theta, but this is not, this does not contribute to the force because there is no force when the field and the current are parallel. And also you can remember that when the field lines are not cut, there is no force created. Right, so that is the that is how you do the calculations. If you have any doubts, please ask me. If not, please do question number 12 as well. Write down the note of that part. If the conductor is placed in such a way that it cuts the magnetic field at any other angle other than 90 degrees, it would have a force weaker than F at right angles. To calculate the force that is generated, we use the following equation: F equals BIL sine theta. F equals BIL sine theta, and I would suggest that you draw this diagram to understand it better. And move to question number 12, so you would understand all the details. We will discuss forces between currents in the next video.